Thanks a lot, everyone, and welcome. Welcome to this session on prioritizing technical debt, as if time and money would matter. So this is a broad topic, and I have a lot of stuff I would like to share with you. So let's start by uncovering the forces we have to balance, the challenges of building large-scale code bases. And these challenges are well captured in something called Lehman's laws of software evolution. So out of curiosity, how many of you have heard about Lehman's laws before? Not that many. That's fascinating. So in my experience, Lehman's laws, they are not that well known, but they are pretty old. They were written down in the late 1970s, early 1980s, and I tried to do my best to popularize them. So today, I want to show you just two of those laws and see if they resonate with your experience. So let's look at the first law, the law of continuing change, where Lehman claims that the system has to continuously adapt and evolve, or it will become progressively less useful over time. Is this something you recognize? Yeah, of course. This is the very reason that we keep adding new stuff, that we keep adding new features to our existing code bases, because we need to keep them relevant, not only to our users, we might have to respond to competitors, right? So what I want you to do now is to notice that there is some kind of tension, some kind of conflict to the second law of software evolution. And that's the law of increasing complexity. Here, Lehman claims that as a system evolves, its complexity will increase unless we actively try to reduce it. And this is the main challenge that we need to fight in order to successfully maintain software. We need to balance those two sides. On one hand, we have to continuously adapt and evolve our code, but as it does, its complexity will increase as well. So we need to find ways of reducing that. And when we fail to do that, what tends to happen in my experience is that we are not always aware of it. Because what we tend to see is rarely the root cause. What we tend to experience are a bunch of different symptoms. And those symptoms, they manifest themselves in different ways depending on who we are. So if we work on the inside, what we will typically see is that we will see effects on the roadmap. We will typically see longer and longer lead times. It takes so much longer to respond to that change. What we also tend to see and tend to experience is a lack of predictability. It gets harder and harder to guess how long it will take to get that important feature in. Now, what our end users tend to see is that they tend to experience effects on the external quality of the code. They tend to see bugs and defects. And the real root causes tend to remain largely hidden and opaque. And I think this is indeed a big issue that we're facing in the software industry. If we have things like code quality issues and technical debt, they're so invisible, right? We cannot pick them up and look at them. So how can we resolve this? How can we bring visibility to things like technical debt? Well, one obvious approach is to start to quantify and measure it, right? So let's have a look at that. This is an approach I've seen several times. As part of my day job, one thing that I do is I go to different companies, analyze their code, and come up with recommendations. And when I started to do that 4 years ago, one of my very first customers that I visited, they had done something very interesting prior to my arrival. They had used a tool capable of quantifying technical debt. So they've taken this tool and thrown it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. Now, 4,000 years, I really like to put that into perspective for you. So 4,000 years ago, that was here. That's the start of recorded history through the invention of writing. So you know, on a side note, I'm always curious what kind of programming language they used. Most likely Fortran, right? All right. I'm getting sidetracked. I do understand that much of that technical debt grew in parallel by having hundreds of developers working on the code base. So that's not my key point. My key point is that 4,000 years of technical debt, how useful is it to know that? It might be interesting, it's definitely depressing, but it's not particularly actionable. So I think it's actually worse than that. I think that there might be some danger to quantifying technical debt. So let me share another story with you. So what tends to happen when organizations start to measure technical debt and try to quantify it is that by using tools, you get lots of data. So the first thing that goes are things like suggested improvements. Get rid of them. Warnings. No, get rid of them. Let's focus on the main issues. Let's focus on everything classified as major, right? So you sum it up, and you typically end up with things like you have 7,000 major issues in your code base. Now, what you do to act upon that is that you specify a quantitative goal. So you say that, all right, let's invest 3 months into bringing those 7,000 issues down to 5,000. Has anyone ever heard that? Yeah, a lot of you nod. I've seen it done several times, and each time I come across it, I always advise against it. And the reason I advise against it is because, to me, going from 7,000 issues down to 5,000, you know, it's a little bit like choosing to jump from the 5th instead of the 7th floor. Most likely, none of them are a particularly good idea. And the reason I say that is because, first of all, we need to consider what kind of behavior do we reinforce with a quantitative goal. What's going to happen if we are measured and bringing it down from 7,000 to 5,000? Well, we're going to do 2 things. We're going to pick the simplest tasks, not necessarily the ones that has the highest business impact. We're also going to pick tasks that we are familiar with. And all those issues that really matter, they're going to be left there unattended. So as a consequence, I've seen many organizations invest a lot of money into trying to pay off technical debt that way. And they basically end up not only wasting time, but also wasting an opportunity to improve something that truly matters. So let's sum it up. I hope I managed to explain why I think that quantifying technical debt isn't actionable. And one of the reasons is also because we always have this trade-off between improving existing code versus adding new features. And it's a balance we need to strike, and it's a balance that's going to shift over time as our product evolves. So how can we prioritize technical debt? How can we find a technical debt that really needs our attention? Well, those of you who might have read one of my books or maybe even listened to one of my previous presentations, you know that I'm a big fan of version control data. So I guess we all have our odd hobbies, and this one is mine. And the reason I like version control data is because as an industry, we have used version control more or less as an overly complicated backup system and then occasionally as a collaboration tool. But in doing so, we have built up a wonderful behavioral data source that tells the story of how our code has evolved and how we have interacted with it. So this is a data source that we can tap into and get lots of information that can help us make better decisions. So let me show you a number of examples. The first example I want to show you is from a code base that I think a lot of you might actually carry around in your pocket as I speak. I'm talking about Android. More specifically, I want to talk about a part of Android known as the Platform Framework Base. So the Platform Framework Base, it's a pretty big code base, around 3 million lines of code, most of it written in Java, and lots of contributors. Now, what you see here on the screens is something called a hotspot analysis. So this is like the foundation of prioritizing technical debt. So let me walk you through it so you know what you see here. First of all, I want you to focus on those large blue circles that you see, the ones that blink on screen right now. Each one of those represents a top-level folder. So this is a hierarchical visualization that follows the folder structure of your code. So if this was your code base, you would recognize the names of those large blue circles as significant subsystems or top-level services or components, something like that. Now, it's also interactive, so we can click on one of those folders and zoom in on the level of detail we're interested in. And once we get to the lowest level, we see that each module with source code is visualized as a circle. And we see that the circles have different size. That's because size is used to capture code complexity. Now, how do you measure code complexity? Well, you might be familiar with things like McCabe's cyclomatic complexity, nested complexity, Halstead's volume metrics, and so on. And most organizations already have tooling in place to measure that. So what I recommend is pick whatever you have. If you don't have anything, then just use the number of lines of code as a proxy for a complexity. Because the truth is, complexity metrics aren't particularly good at predicting complexity. So this is something we really just want to get an idea of how hard is this code going to be for a human to understand. And it's not really that important what metric we use, because this is not, and I repeat this is not the important dimension. Because complexity has this property that code complexity is only a problem when we need to deal with it. So to find out if that overly complicated code really has an impact on us, we need to find out, do we actually have to work with that code or not? And this is data that we can pull out of a version control system. And I tend to use color to visualize it. So I simply look at the change frequency. How often do we do a commit that touch that particular piece of code? And now, when we have those two dimensions, we can combine them and we can identify hotspots. And hotspots are complicated code that we have to work with often. Now, if I take a step back and look at this in terms of technical depth, I have come to view the code complexity as the principal. So this is the loan that we have. But the change frequency is what determines the interest on that loan. And I'm going to come back to that. For now, let's return to Android, and let's look at our #1 hotspot in Android right now. This hotspot is something called an ActivityManager service. Now, this is a DDD conference. What do you think about that naming? It's beautiful, isn't it? Absolutely fantastic. So when I come across a hotspot, the first thing I want to point out is that just because something is a hotspot doesn't necessarily mean it's a problem. So when I come across a hotspot, what I do is I inspect the code. I might use static analysis techniques to look into it and see what kind of issues do we have here. And I tend to emphasize a number of issues that are known to correlate with increased maintenance cost and increased risk for defects. And one of them is that you see here is low cohesion. Our ActivityManager service simply has too many responsibilities. And I don't think that comes as a surprise to anyone who have seen that name, right? Because look at it, manager and service. 2 words, each one of them in isolation signals a unit with low cohesion. Now we combine them, right? So this is expected. I also tend to look for things like deeply nested logic, you know, the dreaded arrow pattern. Because this, if you look at the research, that's a pattern that's responsible for roughly 20% of all defects we will have. So it pays off to detect those issues. Now, the next thing I do, once I have made an assessment of the code, is I want to find out, what about the context? What about the situation here? Because this might be problems that are well known and understood by the organization already. So the reason this code is a hotspot is because the developers are working to improve the code. That could be the case, right? Yeah, I've actually seen that happen. So to find out if that's the case, I use a technique I call complexity trends. And the way it works is that I go to version control history, and then I pull out each historic revision of each of the hotspot, and then I calculate the code complexity at each point in time, typically using something like cyclomatic complexity, something very simple. And as a reference, I plot the blue line, which is the lines of code over time. And if we look at that trend, what we see here is that there is a steady growth in terms of lines of code, which might be a problem on its own. But it's definitely a problem when we see that the code complexity grows at an even steeper rate, because that tends to indicate that the way this hotspot evolves is by the addition of complex conditional logic. So if we take a step back and sum up what we have so far, we have a piece of code that we know is irrelevant because it's a hotspot. We do a lot of work in it. And we know that that work is most likely expensive and risky due to all the quality issues we find in the code. And we know that when we work with it, the code becomes even more complicated. So this is a growing problem. So based upon those data points, I would say that this is a pretty good refactoring target. Now the question is, of course, who would like to have that refactoring task? Because what we have here is 20,000 lines of code in a single file that's been worked on by 74 developers just over the past months. So who would like to refactor this? No one. That's really, really good, because we should never, ever take on large refactorings like that. Because what's going to happen is that we're going to branch out, we're going to spend 3 months on that branch, and we will never, ever be able to merge it back. So we need to break this down and make it actionable. How can we do that? Well, one technique that I use is something I call an X-ray analysis. So what I do here is that when I find those large hotspots, what I do is I parse them into separate methods and functions, and then I look at the Git log, where do each commit hit over time, and I sum it up, and I get hotspots on a method level. And this is something we can use to prioritize refactorings. Let's have a look at the ActivityManager service method level hotspots. The number one hotspot right now is something called handle message. We see in that data that handle message has been modified 98 times just over the past year. So a couple of times a week, someone is working on handle message. We also see that its cyclomatic complexity, the measure of how many logical branches we have, is through the roof, 106 branches, which basically means that you need at least that number of unit tests to cover it. Right now, it has exactly 0. And we also see that it's a pretty big method, 500 lines of code. That's a lot, isn't it? It is. But it's definitely less than 20,000 lines of code, which was size of a total hotspot. And it's absolutely less than 3 million lines of code, which was size of a total code base. So more important, we are now on a level where we can act upon this information and do a focused refactoring based on data from how we, as an organization, have worked with the code. Now, I want to show you one more thing. I want to show you why hotspots work so well to prioritize technical debt, and then we move on to another topic. Now, please look carefully, because this is probably the most important slide I'm going to show you today. This is the reason why you don't have to fix all your technical debt. Now, what you see here on screen, you don't see anything yet, right? I need to click one more time. Let's see. Animations, cool. So, what you see here is an example from 3 radically different code bases. And all those 3 graphs show the same kind of data. On the x-axis, we have each file in the system, and those files are sorted according to the change frequencies. That is, how many commits have you done to that particular file. And the number of commits is what you see on the y-axis. Now, if you look at the 3 examples here, you see they are examples of 3 radically different code bases, targeting different domains, developed by different organizations, different developers, different programming languages, different lifetime spans. Everything is different. And yet, they all show exactly the same pattern. They show a power law distribution. And this is something I've found in every single code base I've analyzed so far, and I think I've analyzed somewhere between 250 and 300 code bases over the past year. So this seems to be the way that software evolves. And this is important to us because it gives us a tool to prioritize. Because what this means is that most of our code is going to be in the long tail. So it's code that's rarely, if ever, touched. That's not where we want to invest in risky improvements. Most of our development activity, on the other hand, is going to be at the head of the curve. And the fascinating thing about that is that even a minor amount of technical debt at the head of the curve is going to be really, really expensive due to the high interest on it for all the development activity. Now, there's another reason why hotspots work well. In fact, I have this subtitle here. I know it doesn't really fit on the slides, but I really like it. It's a chapter from my latest book, where I said your best bug fix is time. And what I meant by that is that I'm quoting a research study. And that research study, what it did was it compared a lot of different software systems, and it found its conclusion was that if you have 2 modules basically doing the same thing, and one of those modules is a year older, that is, the code hasn't been modified in a year compared to another module, that older module has roughly 1/3 of the defects that the new module has. So how can that come? It basically means that old code is good code. And I agree upon that because code grows old for 2 different reasons. The first one is because it's dead code, right? We don't use it anymore. And that's kind of the best code you can have because you can simply delete it and you never ever have to care about any technical debt there. The second reason that code might grow old is because it's stable. It has been debugged into functionality. It's been proven in use. It's been battle tested. It just does its job. So what this power law curve does for you and what the hotspots do is that they also help you identify those stable parts of the code so that you can distinguish them from the more volatile parts. Now, when I talk about technical debt, one thing I have found is that we in the industry, we're often using technical debt and legacy code interchangeable. But they are not the same thing. Legacy code is something different. So I want to make a small detour into legacy code. And the definition of legacy code that I use is this. I use legacy code to describe code that, first of all, it lacks in quality to some extent. And second, and most important, it's code that we didn't write ourselves. Now, why do I want to make this distinction between legacy code and technical debt? Well, let me tell you another story. A couple of years ago, I visited a client and I analyzed 2 of their software systems together with their teams. So we did a hotspot analysis, we inspected the findings, and what we found out was that both of those systems, they looked really, really good. There were some minor issues, but nothing that you couldn't work with, so looked pretty good. And then the team told me, but yeah, you know, we have a third code base as well. So I said, all right, so let's look at that one too. Yeah, but I warn you, it's a complete mess. So I thought, okay, this is getting interesting. Let's have a look at it. So we picked it up, we did a hotspot analysis, and hotspots help us zoom in on a very small part of the code base, maybe 1, 2, 3% of it, so you can inspect it. So we did that. And what we found out, that there was virtually no difference in quality at all compared to the other 2 code bases. The third code base looked equally good. It was equally well written, equally well structured. And at first, this was a bit surprising. But then we looked at, all right, but who has actually written that code? And it turned out that that third code base wasn't written by that team. It was written by a different entity in the organization, and they had simply inherited the code base. So the reason that code was perceived as hard to understand had nothing at all to do with any properties of the code itself. And I found it fascinating, that link between the social and technical aspects. So let's explore that by having a look at how quick can you take your current code base and turn it into legacy code that's impossible to understand. And to do this, we need to figure out how much of the code is written by us and how much is written by someone else. How can we do that? Well, remember, we are in version control wonderland. So our version control system knows exactly which developer that has written which piece of code. So we simply need to sum that up and present it on a file level. Now, for this case study, and to make it more specific, I want to look at a different system. I want to look at another American code base, ASP.NET MVC Core from Microsoft. Now, has anyone worked with ASP.NET MVC Core? Ah, cool. So this is what your code is running on. That's great. Now, the visualization you see here is the same as we used for the hotspots, same visualization style, something called enclosure diagrams, but the colors signal a different meaning. Blue basically means that these are parts of the code that's written by the people who are currently working on that code base, part of the current team. And the different shades of gray indicates black holes in our system mastery. So these are parts of the code that are written by former contributors that might have left the team or maybe even left the company. Now, what you want to do is, this kind of information, it's not particularly useful to get as an after-the-fact event. It can help you get some insights, but it's not that actionable. So what you want to do is you want to use this as a proactive technique. So if some developer is going to leave, what you want to do is you want to look at what's the impact here so that we can act upon it. So what I did now is that I simply pretended that one of the people at Microsoft working full-time on this code base, I pretended that that person is going to leave. And I looked at the Git log and found out in which modules is that person the main developer. And I use red to visualize that. So what you see here now on the next visualization is the impact if a single core developer is going to leave. Now, let's say this really happens. I just made up that scenario, right? But let's say it really happens. The data is real. Should we be worried? Yes, we should. How do we act upon that data? Well, what I do is I use a number of different patterns that I look for. First of all, I look for packages where we tend to lose the majority of the knowledge. So in this case, you see on one highlighted example, something called integration tests, which could be important to us. If it is, what I would do in that case is that I would talk to the other people, the ones who are marked as blue there, who are still contributing, and I would check with them, would you be comfortable in taking over the maintenance of the rest of the integration tests. If they say yes, then problem solved. If not, what I would do then is that I would dig a bit deeper. I would combine the social data with the technical data from the hotspot analysis. In particular, I would look for relevance. Is there any hotspot that is going to be abandoned? If that's the case, then we know it's very likely that we will continue to work on that code. Then we will look at the code quality. Do we have any code quality issues in that part of the code? If we do, then it's very likely to be a real offboarding risk. So based on that data, we can again narrow it down to a few hotspots where we can use the time. That person probably is going to hang around for another couple of weeks before they were actually leaving. So I would use that time to pair them together with someone else and have them refactor that code together to mitigate an upcoming offboarding risk. So the takeaway of this part is that I find it so fascinating that there's so much more to code complexity than just properties of the code itself. In particular, social factors will influence how we perceive a code base. So factors like system mastery are really, really important. And to gather objective data and visualizing it helps us make better decisions and use those and act in a proactive way. Now, before I continue, I want to show you what kind of tools I use, because I do hope you want to try this out on your own code base. So I have to tell you that this is a young discipline, it's a young field, and when I started to work on these techniques maybe 10 years ago, there weren't any tools available that could do the kind of analysis I wanted to do. So I had to write my own. And I open sourced my first tool suite on GitHub. It's called CodeMat. It's entirely free and open sourced. And CodeMat is capable of doing most of the analysis I'm going to talk about. It can do the knowledge loss thing, it can do the hotspots. So that might be a good starting point. What I work on these days is something called CodeScene. So CodeScene is basically automates all these steps. And CodeScene is also available at CodeScene.io as a free service for open source projects. So if you work in that space, please have a look at it and consider to support it. Finally, I also want to point out that I find it so fascinating that you can get really, really far with just a Git client. So I have several examples on that in my book, but I want to show you my favorite here. It turns out that if you do a git log with the -l flag, then you can specify a function inside a file and have Git trace the evolution of that function. So this is like a simple X-ray directly from your command line. Okay. So far, we have looked at two different monolithic code bases, but over the past year, as we're all well aware of, our architectural landscape has changed quite a bit. So over the past years, I've done a lot of workshops around these techniques. And 4 years ago, when I started to do my workshops, many participants, they told me that we have started to look into microservices. We're planning a legacy migration project. But no one was really doing microservices at that time. And now, fast forward just 4 years, and every single company that I visit have invested in microservices. It's been quite a transformation in a very short window of time. And I find that fascinating. And the reason I find that so fascinating is because what this means to us is that tomorrow's legacy systems are going to be microservices. Isn't that exciting? It sure is, right? So I do think it pays off to see how can we take these techniques and scale them to microservices. Well, there are a number of practical challenges with analyzing microservice architectures. And those practical challenges are fairly easy to solve, and I'm going to show you how. The first is, of course, that microservice architectures tend to be polyglot code bases, so many different implementation languages. The second one is that they tend to be structured in multiple different Git repositories, right? But that's also something you can work with. I think that the main challenges of microservices are not practical in that sense. The main challenges are that in a microservice architecture, the most important aspects are not necessarily properties of the code, but properties of the system. And what I mean by that is that in a microservice architecture, it's usually much more important to uncover the fundamental principles, like detecting implicit dependencies between different services. What is the coupling between our different services? That's much more important than if we have a hotspot in a specific service. In a microservice system, the social factors tend to get even more important. So we want to start to look at for things like team coupling and team autonomy. Is that something we can measure as well? So let's have an example on our microservice architecture. Is anyone familiar with this one, Spinnaker? Yeah, some of you. So Spinnaker is a cloud-based continuous delivery platform, originally developed by Netflix and now being worked on by Google as well. And the reason I use Spinnaker for, I don't know much about Spinnaker myself, but I use it for a lot of my case studies because it's one of the few large-scale microservice systems that are open sourced. So what you see here is a hotspot visualization of all of Spinnaker. So what we see here is more than 30 different Git repositories and visualized in multiple languages. And doing a hotspot analysis like that of microservice architecture is really straightforward. So those challenges I mentioned with polyglot codebase, it doesn't really matter because we're using version control data. And one of the beauties of version control data is that it's language neutral. So we get that for free. And the practical challenge of analyzing multiple Git repositories is also pretty easy to resolve. All I do is I just break it down. I divide and conquer. I do one hotspot analysis for each Git repository, and then I just piece them together. So it's pretty straightforward. Now, we can use the hotspot analysis here to identify hotspots and inspect them. And I think that's a good use case. But in microservices, I tend to find that the interesting unit of analysis is the service itself, not necessarily the file level. So what I tend to do is that I take all that data for one service, typically one Git repository, and I just aggregate it together so that I can detect hotspots on a microservice level. And I can do the same thing with the complexity trends. I can aggregate them just by looking at the contributions to all the files that make up a specific service, and I can get the complexity trend for my microservice. And this is something that I have used to help us detect services that grow too complex, which might be an indication of low cohesion and too many responsibilities stuffed into a service. But I do think that we need to do better. Like I talked about earlier, hotspot analysis doesn't really help us in evaluating boundaries. It doesn't help us by uncovering relationships between different services. So how can we do that? How can we analyze dependencies between microservices located in different repositories? The main challenge is that there's no physical connection between them. They're typically decoupled via networks, right? Via message buses. So this is how I do it. This is a dependency analysis of the Spinnaker codebase. And I'm going to return to this visualization, and we're going to interpret it, and I'm going to show you how I typically use the data. But before I do that, I want to reveal how I do to actually calculate those dependencies. I use a technique called change coupling. Has anyone heard about change coupling before? Some of you, but good, I got something new for you. That's really good. So change coupling is fascinating because it's very, very different from the way we typically talk about coupling. When we talk about coupling in software, we typically mean a dependency. I use some code over here. Now those two pieces depend upon each other. But change coupling is different because change coupling isn't calculated from the code. It's calculated from the evolution of the code. So what I do now is that I typically look at the commit messages and find out, all right, which issue, which ticket do we reference in this particular change? And then I aggregate them together into logical change sets across all possible Git repositories. And I try to find patterns in it. So here's how it works conceptually. Let's say that we're adding a new feature to a microservice architecture. The first time we do that, we have to modify the subscription service and the sign-up service together. So then we add another feature, or maybe we fix a bug, and it turns out we have to modify something else. And the third time we do something new, we have to modify the subscription service and the sign-up service together again. So now, if this is a trend that continues, we know that there has to be some kind of relationship between the subscription service and the sign-up service. There has to be some logical dependency between them because they're evolving together all the time. And if that happens often enough, we can conclude that we indeed have a dependency between them, a logical dependency. So what you see here in Spinnaker is a change coupling analysis. So this doesn't show you the dependencies you would see in code. Those dependencies are most likely invisible in the code. What they show you is the change impact. built based on how you, as developers, have interacted with the code base. So if we look at Spinnaker, what I did now was I looked at the bakery service. So we see that bakery, and again, I'm not going to go into the details of Spinnaker. I want to show you on a conceptual level. We can see that when bakery is modified for one reason or another, there seems to be a whole cluster of microservices that are frequently modified together with bakery. Now, the interesting thing with change coupling, and this is why it's my personal favorite analysis, is because change coupling itself is neither good nor bad. It just shows you that this is the way your system evolves. This is how you interact with it. So it's something I use to reason about the cost of change. And the way I use it is that I look at that change coupling and I look for patterns that violate my architectural principles that we have on that particular system. So for example, if you have on microservice architecture and one of your major principles is loose coupling, then this cluster might be a warning sign worth investigating in more depth. And if you do that, you can identify services that can and maybe even should be combined together, or you can detect erroneously drawn bounded contexts. So the next thing I do here, if I want to follow up on this, is that I do a change coupling analysis on the file level, right? So again, you look at what files are changed together as part of the same feature, same ticket. And again, this shows the power of version control data. So what we see here is that we can detect dependencies across language boundaries. So what we have here is a very classic case where you have some part of the user interface. In this case, we're implementing TypeScript. And we see that it's tightly coupled in an evolution to some stuff on the back end. So this is a very common scenario, and it's something I would like to dive a little bit deeper into. And now I have ripped through a number of open source projects, so I think it's only fair that I start to criticize my own code, isn't it? So let's have a look at that. This beauty is from me. This is a part of CodeScene. And I did a change coupling analysis. In this case, what you see here is the file level. And what I found out was exactly the same pattern as I saw in Spinnaker, that we have some code in the user interface done in JavaScript, and we could see that that code seemed to co-evolve with some stuff on the back end, implementing closure. Now, when I saw that, I got a little bit surprised, because I happen to know that the architecture of that application roughly looks like this. That there is some architectural distance between the change-coupled entities. And this is a warning sign for me, because it definitely violates my expectations on the architecture. Things that are distant really shouldn't co-evolve, right? It's very likely to be a surprise. And surprises is one of the most expensive things you can put into an architecture. So I decided to dig deeper. And what I did now was that I used the X-ray technique on change coupling as well. So instead of figuring out which files change together, I look at which functions inside those different files evolve together. And this is what I found. So it turns out, if we start on the right-hand side, on the back end, it turns out that the parts there, the units that co-evolve together with the user interface, those parts, they're actually responsible for part of the analysis pipeline. So these are the parts that are going to fetch that stuff from Git and do the calculations on it. And once it has done those calculations, it's going to populate the result structure. And when I saw that, I understood, that's the reason. So each time we add something there, we add something to the result structure, and we have a predictable modification in the user interface, of course, to present it as well. So it looks like a classic producer-consumer relationship, right? And I start to think that, maybe we can resolve it by using things like composite UIs. Maybe we can start to use smart view models, view models that kind of know how to render themselves. And we could. And if we would do that, we would break that change coupling, and our code would be a little bit easier to evolve. But I do think we miss the root cause by doing that. Because I think the root cause here is, and this is something I've seen in many, many applications, is that separation into user interface in one Git repository and business logic in something else, it's entirely accidental. It's just there because one piece of code happens to be in JavaScript, which our web browser understands, and the other one is in Java or Clojure or something like that, which we prefer on the back end. But the separation is accidental. Those two are logically part of exactly the same things. They're just different views of the basic data. So I would like to leave you with the fact, because I do think that we need to rethink large-scale software architecture in the years to come, because our systems are growing increasingly more complicated. And I have found that we can significantly simplify our architectures by letting features drive architectural building blocks, not technology. And I do think that behavioral code analysis has a place here, because with a behavioral code analysis, like I've showed you today, like hotspots and change coupling and system mastery, is that they help us visualize and detect properties of our system that are invisible in the source code itself. And as such, these techniques, they can help you by helping you focus your precious attention and expertise to the parts of the system that are likely to need it the most. So, I want to leave you with some references. If you want to dig deeper into this, and I hope you won't, then I can recommend Software Design X-Rays, a book that came out last year, where I cover all of these techniques in much more depth and also include some practical exercises and hands-on examples. If you want to read more about it, I blog frequently at Empear.com, where I have a number of case studies. The last one I put up was about React, detecting hotspots there. And if you want to explore some well-known open source systems yourself, then I have a showcase page at CodeScene.io where you have the interactive visualizations. You can play around with them and see what you find. Now, I'm going to hang around for the rest of the conference, and I'll be happy to discuss all of this stuff in much more detail with you. But before I leave you for now, I would like to take this opportunity and say thanks a lot for showing up. I hope you enjoyed it. I definitely appreciate you being here. So thanks a lot for that, and may the code be with you. Thank you.